Hi everyone, I am going to present a generalist Hanabi agent. I am Hadi and this is a joint work with Arjun, Matthew, Jana, Miao, and Sarath. In real-world scenarios, cooperation and coordination among multiple agents are essential for achieving their goals. For example, coordinating different self-driving cars from different companies on the road or collaborating with a population of intelligent drones to perform a task. Hanabi, introduced in 2020 by Bard et al. From DeepMind, has been a popular testbed to evaluate the cooperative capabilities of RL agents. For those unfamiliar with Hanabi, Hanabi is a 2 to 5 player cooperative game where players need to complete firework stacks ranging from 1 to 5 with 5 different colors. During each turn, the player can choose one of the following actions: play a card from their hand, discard a card, or provide a hint to other players. In contrast to poker, for example, the players can see other players' cards but cannot see their own cards, so they must rely on the hints provided by the other partners. The hints can have multiple levels of information. As a result, the players must reason about the intentions of other agents' hints to succeed in the game. The original Hanabi paper observed that while agents trained through self-play could solve the tasks almost perfectly, they performed poorly when paired with another expert Hanabi agents trained using the same algorithm, but with even a different seed. Therefore, several research efforts have been published to address the zero-shot coordination problem in recent years, in which the agents trained independently must coordinate zero-shot. However, all these methods rely on complex multi-agent approaches and are limited to specific game settings, such as the two-player game settings, primarily due to the fact that it requires billions of training steps to train these agents, and if you want to scale this to 5-player, you would require even more training steps. Our goal in this project was to build a generalist Hanabi agent which is able to not only play well with different partners, but also it can play well with in different game settings. However, there are two major challenges. First is the original vectorized observation of the Hanabi environment is highly structured and therefore not flexible. To address this, as text has been shown to improve transferability, we propose converting the vectorized observations and actions to text. As a result, when switching from a two-player Hanabi game to a three-player game, we only observe a few modifications to the textual observation and action, while there are several changes to the vectorized observations in arbitrary places. The second main challenge comes from the fact that when switching between game settings, both the size of observation and action changes. Consequently, the original R2D2 agent used in most of the related work is no longer applicable. To overcome this, we designed R3D2, an agent inspired by deep recurrent relevance Q network architecture. R3D2 takes both the state and action as input and computes the Q values directly for that actions rather than having a fixed number of heads to compute Q values as in R2D2 architectures. Integrating the RQN architectures with distributed learning results in R3D2. We introduced two variants of R3D2, R3D2 single task and R3D2 multitask, which is the first Hanabi agent that can play all Hanabi game settings simultaneously. First of all, in a two-player setting, we observed that R3D2 single task outperforms IQL and other play in all metrics and can achieve a performance close to off-belief learning in both self-play and intra-cross-play, while outperforming off-belief learning in inter-cross-play. What is important is that this is achieved only through self-play pre-training without any zero-shot coordination specific method. So this shows that R3D2 can coordinate well with other partners. Now to show the transferability of policies learned by R3D2 agents to different game settings, we take the agents on the x-axis in this plot and evaluate them in a two-player settings with another two-player expert Hanabi agent. We introduce these evaluations for the first time, and since it's an OOD task, it can be quite challenging. To understand the role of our two modifications to the R2D2 architectures, we also introduce R2D2 text, which is essentially the same as R2D2 but only trained on text input. For both R2D2 and R2D2 text, we mask the illegal action heads to be able to transfer them to another game settings. As we can see, while R2D2 and R2D2 text achieves almost zero transfer performance in two-player setting, R3D2 3-player, 4 and 5 players, which are only trained on those settings, show reasonable performance on a two-player game settings zero shot. If we repeat these evaluations for 3, 4 and 5-player game settings, of course, as the number of agents increases, coordination becomes more challenging, but we can see that R3D2 shows much higher transferability performance compared to R2D2 and R2D2 text in these settings too. Finally, we can observe that the single model of R3D2 multitasks shown by blue bars still perform well on all settings. suggesting that we have developed an agent capable of playing all Hanabi game settings simultaneously. Finally, since text-based Hanabi game can essentially be played by any LLM as well, we evaluated the state-of-the-art large language models with either prompting or fine-tuning them on some expert Hanabi trajectories to assess if we could develop a generalist Hanabi agent without any online reinforcement learning. Our results demonstrate that current LLMs are still far from solving text-based Hanabi. For instance, the O3 model from OpenAI achieved only 12 out of 25 with a reasonable amount of prompting effort. For fine-tuning results, please see the paper for more detailed results. Thank you for your time. Here are the QR codes for the paper and the public repository. Feel free to contact us for any comments or questions.